तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, this will be lecture number 43 on our ongoing series on mechanical measurements. Towards the end of the last lecture, we were actually looking at measurement of concentration of gases using so called non separation methods, and in fact in the previous lecture we have covered already non dispersive infrared analyzer, which is a very useful instrument which is used in day to day laboratory practice for measuring especially exhaust gases from IC engines. The second one I was trying to describe in some detail was the differential absorption LiDAR. LiDAR stands for light detection and ranging, and the particular technique is called dial or differential absorption LiDAR, and we were looking at it. So, we will resume that and then come back to this slide to see what we are going to do subsequently. So, I was explaining the principle of the LiDAR, the differential absorption scheme. So, the basis is of course called the Beer's law, which assumes or which postulates there is an exponential decrease in the intensity of light which passes through an absorbing medium. In this case, we are looking at a particular wavelength at which some absorption is expected of a particular gas which is existing in some concentration within that medium. There may be other gases present which are not going to be influencing the absorption process. For example, if you remember, I talked about the lambda on and lambda off. Lambda on is the wavelength or the frequency at which the light will be absorbed by the particular gas which I am interested in. It may be water vapor, for example, or carbon monoxide, carbon dioxide, any of the gases which may be interested. And I have lambda off is the frequency which is very close to lambda on, but it is such that there is no appreciable absorption by the species at that particular wavelength or frequency. So, differential absorption means that there is a difference in the absorption capability of the particular gas, because these two wavelengths have this particular property. One wavelength is absorbed, the other one is not. So, let us look at what is going to happen to the light which is passing through the medium. So, I have given here the L is the thickness of the medium or the extent of the medium. The incident radiation is I naught at a particular wavelength which is of interest to us, and what is leaving this absorber is IL. IL is the intensity as it leaves the layer whichever I am looking at, layer of medium which may or may not absorb depending on the frequency of the radiation. So, the Beer's law states that IL by I naught, the ratio of the emerging intensity to the incident intensity is e to the power of minus c. C is the concentration in numbers per meter cube of the particular species I am interested in. Sigma absorption is the absorption cross section, and L is the length of the passage through the medium. In fact, I have to add something else to the sigma absorption. In practice, what will happen is there may be other processes which take place, processes other than absorption. What are these processes which may take place? One of them is of course scattering. So, in principle what I have to do is the sigma absorption I have to augment by the scattering process. So, it is usually additive, because the concentration we are talking about is very small, it is usually additive, and therefore, we can replace this by what we call a sigma total, which will be sum of sigma absorption plus sigma scattering. So, if you see here e to the power of minus c into some summation of two quantities here can be written as e to the power of, you can see what we can do. Let me write it in the next page. So, I have I L by I naught is the ratio of the two intensities equal to exponential of minus n, I think C is the concentration, multiplied by sigma. So, I will add these two, sigma absorption plus sigma scattering multiplied by L, and this can be written as e to the power of minus C sigma multiplied by exponential of minus C sigma scattering times L. So, suppose I write similar equation for both the on and off frequencies. So, we will see that I L, so this will be lambda on divided by I naught lambda on will be the same expression e to the power of minus C sigma absorption L multiplied by this quantity, whereas I L off divided by I naught off will be, this will be absent, this will be simply given by e to the power of minus C sigma scatter multiplied by L. This concentration is different from this concentration, maybe for example, it could be, it could include also other concentrations of other species which may scatter. So, in fact, I could have written a C sigma absorption plus another C sigma scattering. So, that is not very important to do that. So, we will just see what is the basic idea. Basic idea is that the attenuation, this the ratio is called the attenuation, is proportional to this is the extra term. At the frequency of interest there is an extra attenuation. So, this particular beam which travels the medium and consists of radiation at frequency lambda on or wavelength lambda on suffers a certain extra attenuation. So, this is what we call as extra attenuation. So, if I take the ratio of these two quantities, in fact, what I get is this quantity e to the power of minus C into sigma absorption multiplied by L, and if I know the quantity C absorption cross section and if I know the length of travel within the medium, I can determine what the C is. C is actually logarithm of the other quantity, you can just take it. So, we can, what we can do is, so we will say this is a ratio 1 and we will say this is ratio 2, R1 and R2. So, if you take the ratio of these two, this common factor will go off and you see that R1 by R2 will be actually e to the power of minus C sigma. I, instead of giving that as subscript, I will just imagine it is already there. So, we will just simply write it as C sigma L, or if I take logarithms C will be equal to, so minus C will be equal to, so 1 over sigma L logarithm of R1 by R2. Since R1 is smaller than R2, this will be itself a negative quantity and therefore, minus C equal to this, that minus will cancel, this will give the concentration. So, basically the method of differential absorption consists of determining the ratio of the two quantities R1 and R2. Suppose I assume that both the intensities, if I look at the previous page, if I assume that both the intensities of I naught lambda on and I naught lambda off are the same, if I am able to arrange that, then ratio R1 by R2 is also equal to I L lambda on divided by I naught I L lambda off. So, the ratio of the numerators in these two will also give the R1 R2. So, if I am able to get the same intensity or tune the or adjust the intensities of both the radiation leaving to be the same value. So, let us with this basis let us look at the schematic which I showed in the last lecture. Let us look at the schematic and let us see what are the constituents of this particular measurement technique. So, we have a pulse of laser, in fact there will be pulse lasers, two lasers, one which is going to be lambda on, the other one lambda off. So, both of these pulse lasers will be sent through the atmosphere. So, in this case I have made some arrangement, there is a mirror and there are another mirror here, so that the beam is sent in the direction of my interest. So, the two beams of pulse laser are going to, pulse laser means the laser is characterized by certain pulse width in terms of the duration, and we are usually talking about very small short duration pulse width and maybe at a repetition rate which is a few hertz. That means that the laser is sent again and again. So, we can also measure the returning radiation again and again and then average over several such pulses, so that I can improve the signal to noise. That we will talk about it a little later. So, I have two pulse lasers which are now going in the direction, and here is where I have the gas whose concentration I have to measure. So, let us look at what we can do. The light which leaves the pulse laser, it takes a certain amount of time to travel up to this. Okay. So, it takes a certain amount of travel time and then it starts returning. It will start returning from here and then it will go to the smoke. Some backscattering will take place if there is a cloud or something like that, and therefore, it is going to return from here. So, it takes certain amount of time for it to go and come back. So, if I make the measurement or if I make the measurement of the return signal after a time delay, I can adjust this time delay such that I can sample the region which I have shown here. So, I will choose the time delay such that, and also the gate, the time over which I am going to make the measurement, I will do such that I can specifically find out what is happening in this particular region between these two dashed lines which I have shown here. Okay. So, what happens in this case, the return signal follows the forward path and it comes back and it is gathered by a concave mirror, usually it is in the form of a telescope, and it is gathered by the concave mirror and then reflected, and the two beams are going to be detected by the detector. Okay. So, let me just go through once more just to make clear that we understand what is happening. Two pulse lasers, two pulses with same pulse width and same intensity are generated here. It is sent through the atmosphere whose where I want to make the measurement of the constituent of interest to us. It is reflected back by some object, maybe you can even arrange some kind of a target there which can reflect it, maybe a flying aircraft can reflect it, and then it comes back and then it is gathered by this concave mirror, because the return signal is very weak. The pulse which is going is very strong, but when it returns only a small fraction will be returned, because it will be scattered into all directions and the beam will be expanding, and therefore, the intensity is falling, and therefore, what is coming back is a small percentage. Therefore, in order to get a sizable signal, I have to gather the radiation over a large area. Therefore, I have a large concave mirror to concentrate all the radiation onto the detector, and the pulse duration and the duration between pulses, these are under my control, and also the duration over which I can make the measurement is in my control. So, I can choose a certain window in between two pulses such that I can sample the particular this region, for example. Of course, this region can be shifted accordingly we have to shift the duration over which we are going to make the measurement. So, the pulsed lasers, then the return signal, the detector. The detector has to be very sensitive because we are talking about very small intensities of back returning signal, and the detector must be capable of distinguishing one lambda from the other. So, you must have a detector or a detector pair which is going to measure these two, or of course, these two pulses can be sent with a small time difference, and the detector can detect the two one after the other, and then the ratio can be taken. Okay, let us look at a typical example, a LIDAR atmospheric sensing airborne water vapor measurement. In this case, we are interested in making the measurement of water vapor in the atmosphere. The experiment is called LASE or LASE for LIDAR atmospheric sensing experiment, and conducted by NASA. So, the amount of water vapor could be between 0.01 gram per kilogram to 20 gram per kilogram. Can I go to this please? Yeah, aerosol backscatter ratio can be measured from ground to 20 kilometers. I am talking about the distance over which this measurement can be done, and a resolution of 30 meters. That is what I was talking about. I can find out, I can decide the particular region in which I want to make the measurement, and the resolution is 30 meters vertically and a horizontal resolution of 40 meters. So, that means I can choose the region over which I can make the measurement. The details are actually given in the website which is given here. If more details are required, one can go to the website for details, but I am going to give some characteristics which are again taken from the same website. So, the energy of both the on and off laser beams is 150 millijoule, that is the amount in each pulse. Line width is 0.25 picometer. So, the line width is very small, very narrow. Repetition rate is 5 hertz, one every second there are 5 pulses which are transmitted. The wavelength is 813 and 818. So, you see that they are very close to each other, just with a 5 nanometer difference. One of them is absorbed by the water vapor, the other one is totally transparent to the water vapor. The beam divergence is 0.6 milliradian, pulse width is 50 nanoseconds. So, we are talking about very small narrow pulse width, and the aircraft altitude is 16 to 21 kilometers, and the aircraft velocity is something like 720 kilometer per hour or 200 meter per second. So, in this case the measurement is done from the airplane, the aircraft is going to do make the measurement. So, the receiver, what are the things which are required in the receiver, and as you can see, the receiver has an area of 0.11 square meter, which is a large area, and the field of view is 1.1 milliradian, and the bandwidth is 0.4 nanometer during daytime, and this measurement is done both during daytime and night time. I think some of these the details will be difficult to, it will take too much time for me to explain. These are, you can just go through the website and learn more about these aspects. So, optical transmittance values are given as 23% during daytime and about 49% during night time. Detector is 80% efficiency. The detector used is called avalanche photodiode, and it is a silicon material basically with doping, and it has got a quantum efficiency of 80%. That is what this detector efficiency means. The noise equivalent power is very small, you can see, that means it is very highly sensitive. The smaller the value which is given here, the larger is the sensitivity, and the excess noise factor is 2.5 for the APD. So, to recapitulate, what we are trying to do is to measure the ratio R1 by R2, the two pulses are sent through the atmosphere, and then the concentration is pulled out from this, and the concentration values have already given in the specification. So, the next quantity next technique I am going to look at is given here, the chemiluminescence for Knox detection. So, let us look at this in some detail, and what I will do is I will go to the board and explain some of the things which are involved. NOx measurement. I think we already explained to some extent what this NOx is. Actually, nitric oxide plus nitrogen dioxide, this is referred to as NOx, and it is produced in combustion devices during combustion, and the nitrogen, because nitrogen oxides are formed, nitrogen either comes from the air or it may come sometimes from the fuel also. Fuel might have some nitrogen in it. So, we are not really bothered about where the nitrogen comes from. What we are interested in measuring the NOx. So, the method of measurement is called chemiluminescence. Chemiluminescence. What does it mean? Chemi means chemical, this means light. So, chemical reaction gives rise to light. So, the chemical reaction is the reason for the light. Let us look at what is some of the details. So, if I have a mixture of nitric oxide and nitrogen dioxide, what I can do is I can convert this all to NO. That means that NO is already there. There is some NO2 in the sample gas. I want to convert everything to NO, so that NO plus NO2 is equal to NOx. So, I am converting everything to NO. That means that when you convert the NO2 to NO, this is like equivalent to NOx. So, if I convert all the nitrogen dioxide to nitric oxide, this is a reduction reaction. NO2, there is two oxygen, NO there is only one oxygen, I have to reduce the NO2. How is it done? It is done very simply by heating to high temperature. So, if I heat to high temperature, nitrogen dioxide is converted to nitrogen oxide. Even if I cool it subsequently, it does not become NO2 again, because it takes a long time for that to happen. Therefore, essentially if I perform a chemical reaction by heating, just heating, I will get nitrogen oxide. So, nitric oxide, and now I have converted, let us say in the first step I am going to take the mixture of NO and NO2 and convert to nitric oxide. So, now I am going to find a method of measuring NO, and that actually is done the following way. So, if I take nitrogen oxide and if I react it with ozone O3, I will get NO2. So, of course, one will ask me why we converted NO2 to NO, and now we are converting everything to NO2. The first reaction is to convert everything, so that you are going to measure directly the NOx. The second reaction is to produce NO2, because in this reaction which is taking place is exothermic, and therefore, NO2 is in the excited state. It is in the excited state and it emits radiation, and this emission of radiation is actually called the chemiluminescence. So, chemiluminescence is nothing but the emission of radiation by nitrogen dioxide in the excited state. How did it reach the excited state? NO was reacted with ozone, and because it is exothermic, the reaction leads to nitrogen dioxide, and the nitrogen dioxide is already in the excited state, is in the excited state because of the exothermic reaction, the high temperature, the temperature goes up because of that, and this emits radiation, and therefore, now let us see what happens. So, finally we have NO2 in the excited state. Of course, not all of them will be in the excited state. At any particular temperature there is an equilibrium, the excited state will have a certain concentration, certain number of these are going to be in the excited state, and they are going to jump to the ground state by emitting photons or emitting light of the characteristic frequency, it is the infrared part of the spectrum. So, if I measure the amount of emitted light, of course, the excited state all of them are not going to come to the ground state, they will, some of them are going to come to the ground state, and in this, during this process certain amount of light is emitted. So, what I have to do is to measure the intensity of light which is emitted, and that can be related to the concentration of NO2, which will be related to the concentration of NOx. So, we work backwards and go back to the NOx. So, this is one part of the story. Suppose we want to measure nitric oxide separately and nitrogen dioxide separately, that also can be done, because at low temperatures nitrogen dioxide remains as nitrogen dioxide and nitric oxide remains as nitric oxide. There is these two components are separately available. For example, I can measure NO2 direct from here separately by some other method, may not be the chemiluminescence method, so that I can measure NO and NO2 separately, or you can use the separation methods like what we are going to talk about a little later. So, the chemiluminescence detector or detection of NOx depends on the conversion of NO2 to NO, so that you get NO plus NO2 mixture becomes NO completely, and then allowing it to react with ozone to form nitrogen dioxide in the excited state, measure the amount of radiation coming out of the nitrogen dioxide in the excited state and relate it to the concentration of the nitrogen NOx in the sample. So, this is the chemiluminescence method, which is very often used in the laboratory, and chemiluminescence NOx measuring devices are available ready made, and it is supplied by various manufacturers, and one can just buy it and use it. All these things which I talked about, the conversion to NO2 to NO and the ozone and so on, everything is done in the instrument totally. So, let us look at the next thing which we are going to discuss. So, we have discussed non-separation methods, most of them. In fact, there are many other methods which we do not have simply time to discuss. So, let us look at the separation methods. Separation methods, of course, there are two which we can call as separation methods. One is gas chromatography and the other one is RSAT gas analyzer, which I will come to a little later on. So, let us look at the gas chromatographic method of separation of the species and the measurement of these by using a suitable detector. So, the gas chromatography, the method can be explained by the following kind of schematic. So, the gas chromatograph depends on several factors. One, we need a carrier gas, for example, helium, hydrogen, nitrogen, argon, these are all carrier gases which can be used. So, the carrier gas is going to be mixed with, or the sample gas is going to be mixed with a carrier gas. So, the carrier gas flow is controlled by using a flow controller here, and just a valve, and there is a source of carrier gas which is usually in the form of a cylinder containing high pressure carrier gas, and of course, there should be a regulator, so that I can send it in at the required pressure, and it goes through the flow controller, and the amount of flow is controlled by that one. And the sample gas is added to, the sample gas contains the gases whose concentration I want to measure. That means that the sample must be collected somehow, and it must be brought to this place, and it must be mixed with the carrier gas, and what happens after that. So, we have at this point we have the mixture of sample gas and the carrier gas, and it goes through what is called a separation column. So, I will explain the separation column and how it works a little while from now. So, let us assume that it enters this separation column, which is shown schematically by this loop. In practice, this loop consists of several meters of a small narrow tube, which is referred to as a capillary, and the capillary has got either a porous layer on the wall inside of the tube, or it could be coated with some material which absorbs the gases. So, adsorption means the gases have a tendency to stick onto the wall. Okay. If it is porous also, it will go through the pores and will get stuck there. Okay. And what happens is, when you send a mixture of gases and the carrier through that, the carrier keeps continuously flowing, because the carrier is always there, and the sample, a certain amount of small amount of sample is allowed and it stopped. So, you are now, in other words, introducing a small amount of sample into the carrier gas. So, carrier gas is moving all the time, and a sample gas, small pulse of sample gas is introduced. And what happens to the sample gas? The sample gas may consist of several components. Some of the components may be easily absorbed, some of the components may be difficult to absorb. So, depending on their capacity to absorb, to be absorbed by the surface, they will migrate through this separating column. Even though it is not in the form of column, it is called a column. It is in the form of a loop here, for example. It is a column because the inside it looks like a column, because it is a very long one. And when the sample gas moves through that, the different constituents of the sample gas will move through this column at different velocities. They will move through at different velocities. That means, at the other end of the column, the one which moves fastest will come first here. Okay. So, next the one which moves a little slower than that, and the one which is slower to that, and so on. So, the appearance of the gas here will, if you look at the gases coming out here, it will be carrier gas plus the most high speed gas, the one which moves at the fastest speed will come first, and then after a gap the next one will come, because we have introduced a sample which is in the form of pulse. So, the first one to come will be the gas which moves fastest through the column, the next, after some time, the next gas will come, and so on. So, what happens is, by the time when you come here, the gases are coming as separated species. So, if I have a detector here which detects the presence of the gas other than just the carrier gas. So, there must be some difference between the carrier gas and the sample gas, or the constituent which I am interested in, which should be which should be detected by the detector. That means that the carrier gas, let us say, has some property, sample gas must have the same property, but a slightly different magnitude. So, I will refer to this a little while from now. So, the detector will now sense the presence of different species, and if you record the species coming out, first the lightest gas, then a little heavier gas, and so on and so forth will come here. So, you see that what you are seeing here is a chromatogram. This is called a chromatogram. The axis here is time, and what you see here is the concentration of the gases, the one which came first, the one which came next, one which came subsequently, and so on. So, they are separated as peaks here. So, the area under this peak will be proportional to the concentration of the gas in the sample. Okay. Let us look at some of the details. There are different ways of detecting the gases as they come out of the system. So, different detection techniques are possible, and I have just given a few examples in this slide. For example, thermal conductivity detector. I can use an infrared spectrometer. If you remember, in the last lecture, I talked about the spectrum of various gases, and I showed that they have specific areas, specific wavelengths at which they will absorb, specific bands in which they will absorb. Therefore, if you use an infrared spectrometer, by finding out where the absorption is taking place, I know what gas it is, and also by measuring the amount of absorption, I can immediately say what is the concentration. You remember what we said, Beer's law we talked about just a little while ago. The Beer's law says that the absorption is exponential. So, the amount of absorption is exponential and depends on the concentration and the path length. So, exactly same thing can be applied if you use an infrared spectrometer which can measure the gas concentration. Then we can use a mass spectrometer. Mass spectrometer is where you measure the weight or the mass of the species, and mass spectrometer will separate out the species in terms of their masses. Of course, much more complex than what I am just trying to infer. Mass spectrometer can be in principle used, or you can use what is called a flame ionization detector. So, this will again give a characteristic emission, and that can be used to determine, just like in the case of chemiluminescence detector, the light emitted can be used for detection. But what I will do is, because the details are, there are too many details and these are very complicated things which require a lot of time to discuss, I will just take one detector which is very easy to understand, and we will look at the thermal conductivity detector in some more detail than in the other cases. Okay. So, the infrared spectrometer, mass spectrometers are advanced techniques, and they can be used, and mostly these are used when you want very fine measurement involving very low concentrations. Thermal conductivity detector is useful when the concentration is not very low, but infrared spectrometer or mass spectrometer and so on can be used when the concentration is extremely low. Very trace amounts if are present, we can determine using these spectrometers of various kinds. So, we will look at the thermal conductivity detector in some detail, and that requires a little background on the process which may take place. So, if you look at gases, the different gases have different thermal conductivities. This is a very important observation. So, gases, some gases have higher thermal conductivity than others, and let us look at some of the typical gases which meet with in practice. For example, if I take air as 1, so the whatever is the thermal conductivity of air, I will just take it as the basis. Actual thermal conductivity of air is about 0.025 watts per meter Kelvin, but here I am making it 1. So, what I am trying to do is to find out what is the relative thermal conductivity of different gases with respect to air. So, if air has got thermal conductivity of 1, what is the thermal conductivity of the other gases in terms of air thermal conductivity? So, this is the ratio. Okay. For example, if I take argon, it is less conducting than air, it is about 0.63, and I will come to how this can be used for detection. Carbon dioxide is 0.55, this is all at one temperature, maybe at 0 degrees Celsius or 25 degrees Celsius, usually it is either 0 or 25 degrees Celsius is quoted, and carbon dioxide is 0.55. Carbon monoxide is having a higher thermal conductivity, therefore it is 0.88. So, it is closer to air than carbon dioxide. Therefore, because these two have different thermal conductivities, I can distinguish carbon dioxide and carbon monoxide if I can have a detector which will detect the difference between the thermal conductivities. That is the basic idea. Chlorine is 0.3, ethane is 0.69, ethylene is 0.65. You see here carrier, this is used as a carrier gas helium. It has an extremely high thermal conductivity of 5.42. So, it is 5 times as conducting as air is. So, 5. If you take hydrogen, it is even more so. You will also notice one thing if you are careful, that the lighter the gas is, the smaller the molecular weight, the higher the thermal conductivity. That is what you will see here. For example, helium, hydrogen is a very light gas, it has got a very high thermal conductivity 6.39 as compared to 1 for air. Nitric oxide is 0.90, then nitrogen, it is also used as a carrier gas. Actually, what is the difference between air and nitrogen? Air and nitrogen, the air contains a large percentage of nitrogen and some smaller percentage of oxygen. And if you see here, oxygen is also more or less like 92. So, more or less like that. Of course, the air may contain other constituents, therefore, it is equal to 1. So, nitric oxide 0.9, nitrogen 0.92. Of course, if you see here nitrogen and oxygen, I cannot distinguish using thermal conductivity, because they have more or less the same thermal conductivity. Therefore, oxygen cannot be monitored using the thermal conductivity as the basis. So, let us look at the other thing. Nitrous oxide is 0.57, sulfur dioxide 0.31, and water vapor is 0.63. And why I have included points, the water vapor is that in most combustion devices water vapor is also present in the form of steam or water vapor, and therefore, that is also of interest to us. So, let us see what we can do, how we can use this information. So, for that let me just go back to the try to explain it by showing what is going to happen. Suppose I have a filament, so heated filament, actually we have come across this thermal detection earlier when we were talking about pressure transducers and so on. We have already discussed some of these issues, but just to recapitulate I am trying to look at it again. So, I have a heated filament, that means I am passing a current through that, and now I make the gas flow across that. So, let us make one more sketch, similar one, identical filament, and I have the identical current. I am having another flow here, and let us say this is carrier gas, one of the gases which we had. For example, I can have helium or hydrogen, just to take as an example, and I have here carrier gas plus another gas, for example carbon dioxide. So, I have a small percentage of CO2 being carried by the carrier gas, and let us say that this CO2 is from the gas chromatograph. So, I have a sample of gases, a gas sample taken from some in some particular application, and I have sent it through the gas chromatograph, and at certain time the gas coming out is actually a mixture of carrier gas and CO2. Okay. So, the carrier gas, for example hydrogen, has a very high thermal conductivity, as you saw in the previous slide. We showed the high value of carrier gas, but if I put a small amount of CO2 into it, the thermal conductivity will come down. Okay. The thermal conductivity will come down, and therefore, this K is, let us say K is higher and K is lower here. The K is here higher than the value here. So, suppose I say this K carrier, this is K carrier plus CO2, this is lower than this one. Therefore, the heat transfer from the heated filament to the flow, assuming that the flow is identical, the same flow rate, and I am assuming that the flow is maintained more or less identical, the passages are the same, then the heat transfer from the carrier gas CO2 mixture will be smaller than that in the case of carrier gas alone. Therefore, there is a small change in the heat transfer, Therefore, if I am having the same current and so on, this filament will tend to heat up. So, the temperature of this, let us say Tf2, this is Tf1. So, Tf2 will be greater than Tf1. So, you see that we have a very interesting case here. Suppose that these two filaments are made part of a bridge circuit, then if both of them had carrier gas passing around them, they will be having the same resistance, and therefore, they will be balanced. So, when I have a gas consisting of carrier plus CO2 or carrier plus another gas, and in this case carrier only, there is a slight difference in temperature because of the heat transfer being or heat transfer rates being different for the two filaments. Therefore, it will, because the temperature changes and because the resistance of the heater element is dependent on the temperature, it is just like a RTD or resistant temperature detector, the temperature changes, because of the resistance will change, because the resistance changes, the balance of the bridge will be, the bridge will go out of balance, and the out of balance voltage, which is a small value, can be amplified and it will be proportional to the concentration of the CO2. Let us look at the how it is going to come out. So, let us look at the thermal conductivity of a mixture of hydrogen and carbon dioxide, just a schematic. So, if I put percent of hydrogen in the mixture as the x axis and the thermal conductivity in watts per meter degree Celsius, you see the, if it is percentage of hydrogen is 0, that means all CO2, the value is around here 0.015, something like that. And if I go to 100% hydrogen, you see that it is all 0.17 or 165 or something like that. So, if I draw a graph through, draw the all this data which is available, if I pass a curve, you see that for very close to 100% hydrogen, that means that I have a small percentage of carbon dioxide in the mixture, it is more or less linear. That means that the thermal conductivity change between the carrier gas and the carrier gas plus CO2, which I was talking about earlier, is a small amount, and in that range I can use a linear relationship between the thermal conductivity and the percentage of CO2 in the mixture, because 100% hydrogen here means 80% here means 80% hydrogen or 20% carbon dioxide. So, in other words, I can say that 100 minus whatever value, that gives you the percentage of CO2 here. Okay. If it is 95%, that means 5% CO2. So, the thermal conductivity comes down very slightly, very slightly. That means that the resistance or the temperature is going to change by a small amount, and if we have sensitive detection, we can determine or detect this temperature difference in terms of a change in the resistance, okay, as we were talking about earlier, and this change in resistance can be monitored and related to the concentration of the CO2 in the mixture. For example, let us see how it is going to be done in a thermal conductivity detector. The schematic is shown here. So, the thermal conductivity detector consists of 4 identical heater wires, 4 identical wires, and this is put in a block. This whole thing is put in a block, and the block is kept at a uniform temperature. Okay. All the 4 detectors are in a block, and the block is maintained at a given temperature, at some constant temperature. Okay. Let us see what happens. Now, I have the carrier gas passing through these 2 elements, these 2 heater elements, and the other 2 heater elements are going to be exposed to carrier plus sample. Sample means it is, in this case we are talking about CO2, it may be any other gas which we are trying to ascertain the concentration of. Okay. So, we have the carrier plus sample going through these 2, and they are in the opposite sides of the bridge circuit or the Wheatstone bridge circuit, and these 2 are on the other side of the Wheatstone bridge circuit. Okay. So, these 2 are exposed to the carrier gas alone, these 2 are exposed to the carrier plus sample gas, and the rest, the outside whatever I have shown as this yellow background is actually an isothermal enclosure or a block, it is called a block. So, why do we have an isothermal block? Let us explain it slightly. So, we have 4 heaters, 2 of them exposed to the carrier gas, and what happens to the heat which is generated by the filament? It has to be transmitted from the filament to the block. So, the block temperature is not changing, the block temperature is constant. Therefore, the amount of heat transfer from the filament to the block will depend on the temperature of the filament. Therefore, if one of the filaments is at a higher temperature, more heat will be lost from there. Okay. But the block itself will be at almost the constant temperature, because it is a very heavy mass which is maintained at a constant temperature. Therefore, it provides a heat transfer environment for the detectors. So, these 2 which are exposed to the carrier gas will be at a slightly lower temperature with respect to carrier plus sample. If the sample when you add to carrier reduces the thermal conductivity of the mixture. Okay, that is very important. The carrier, if it has got a very high thermal conductivity and the sample gas has a very low thermal conductivity, it will reduce. It will be otherwise also. If the carrier gas has a low thermal conductivity and the gas you add is going to have higher thermal conductivity, it can be in the other direction. But here we took the case of helium or hydrogen. They have very high thermal conductivity with respect to the other gases, and therefore we are expecting the carrier gas plus the sample to have a lower thermal conductivity, and therefore these two filaments will be at slightly higher temperature, and immediately you see that an imbalance will be set up between these two terminals and an imbalance voltage will appear here, and there are some other adjustments here, zero adjust, because all these four may not be exactly identical. So, the zero adjust is made here, so that we can take care of the adjustment. When all the four elements are exposed to carrier gas, then there should be exactly zero output here. So, this can be adjusted by the zero adjust here, and the power supply, you can see here I have shown some moving contact here. The voltage which is impressed on these two, to this point and this point, can be varied to suit the requirements. Okay. There may be also feedback and so on, I do not want to complicate the whole thing. So, the essential part is that these four detectors which are put in this particular fashion, two exposed to carrier, the other two exposed to carrier plus sample, they are on opposite sides, opposite arms of the bridge, and therefore it actually amplifies the difference. The voltage difference between these 2 points is twice if it were not in this particular fashion. Okay. So, we are going to get a larger the imbalance, and this is detected, and the limit of detection is about 400 micrograms per meter cube. That is the typical number. Okay. Typical number of 400 micrograms per meter cube. Let me just complete this by showing you what we expect in the case of a GC detector. So, let us assume that we have a GC is assumed to be handled arranged like this. You have the carrier, this is sample, then it goes through the separator or separation column, and then what comes here is different gases, and therefore, if you look at the output, so this is the time axis, and this is the TCD output. TCD is thermal conductivity detector output. So, initially it is only the carrier gas, and therefore, carrier gas is having a very there will be no output, and after some time the first gas which is going to separate is going to come out, and it will give you a peak like this. So, this is gas 1, and then there will be no activity for some time, and after some time you will see that there will be one more peak, gas 2. Of course, the height of the peak and the area under the peak will be based on the amount of the gas present, and after some time again you will get a gas 3 and so on and so forth. This may be after 2 minutes, this may be after 5 minutes, this may be after 6.5 minutes, and so on and so forth. So, the gases come out of the gas chromatograph column spaced in time. That means that this is the initial time at which you are going to introduce the gas to the column. This is when we introduce the sample, and then after 2 minutes the first gas has appeared and a small concentration is present. Of course, the gas concentration depends also on the thermal conductivity ratio. So, we have to correct for the thermal conductivity of the particular species, or we can do the following. We can calibrate the instrument with different mixtures with different gases and find out what is the output for a particular gas, and accordingly we can find out what is the scale factor for that particular gas and then introduce that in the interpretation of the quantitative interpretation of the signal. If you just look at the peaks, all you know is that these gases are present. If you want to quantify this, then you must know the gas, the thermal conductivity of the gas must be known, and how it affects the output of the TCD output, that must be known, so that we can calibrate with different mixtures, and these mixtures are ready made and available from manufacturers, so that you can use them for calibration. For example, if I want to calibrate for CO2, I must have a carrier gas plus a certain known fraction of CO2, maybe 2 or 3 different concentrations, and use that and calibrate the instrument, so that I can get quantitative measurement is possible of the gas concentration using the known gas concentrations in the gas, which is gas mixture, which is supplied in a pure form. And of course, purity is very important, because if it is impure, the whole thing, the idea of calibration will become meaningless. So, to just to recapitulate what we have done in the lecture today, we have looked at the first technique we looked at was remote sensing, and remote sensing of particular species to interest to us, which was done by using a lidar, and you know lidar is also used for range finding, or finding the distance between a station and an object in which you are interested, for example. So, how is it done? It is done by finding out how much time it takes for the signal which leaves the lidar to return. So, the time difference between the forward emitted laser and the return signal, that can be linked to the time between these two pulses can be linked to the distance, because we know that the speed of the light in the atmosphere is more or less like equal to 3 into 10⁸ meter per second. So, that is the speed of light. So, we can find out how long it takes to go and come back, and therefore, we know how to calculate the range. So, lidar is simply to determine the range of a particular object from the ground level or wherever you are situated. In this case, I am in other words, what I am doing is I am trying to find out the time. The time contains the distance information, and the change in the intensity contains the concentration information. That is how you separate out the location, that we talked about the specific thing, we talked about some 20 meters or whatever it is. That means that over the 20 meter, which can be situated at different distances from the lidar. So, we can determine the concentration in windows in certain locations, specifically determined by the ranging part of the lidar. So, the dial consists of lidar and also the differential absorption, and that is how you do that. Subsequently we talked about the gas chromatograph, which is going to be which separates the constituent gases into separates them into gases, and they come out of the instrument at different times, and by thermal conductivity detection we can find out how much is the concentration of a particular gas of interest to us. We also talked about the Knox analyzer, which is specifically a chemiluminescence method. I think we will stop here and we will continue the next lecture. Thank you very much.